So the expected time only increases. So it's going to the amount of time it will create. And it's just making it need that as a part. All right, cool. Oh, I think it's like the one closest to me. Okay. I guess maybe none of them are on right now. Oh yeah, I guess there's a delay.
Hello, Shiva.
I'm the biggest culprit. I forget to use this when I have questions.
It's very easy to forget to use these things. Unless like, yeah, unless you can like go and like run.
It's like I have a burning question. I can't think of all these other things.
Yeah. You need like a dedicated person to go and like run the mic to people. I guess that's the challenge. This is a really cool room. I guess the only downside is, I guess you like, because the ceiling is so high, I guess you probably can't have like ceiling mounted mics, right? Because no, I'm just saying like that's a very common thing, right? For like conference rooms is to have like like overhead ceiling mounted mics, so that you don't have to like run the mic to people in the audience. But I'm saying like this is perhaps like too tall.
Like in Simon's they have that.
Yeah. Simon's worried about that. Yeah.
Actually, I haven't seen many rooms having that here on Graduate Campus.
I don't think it's necessarily. Wait, is this on? Wait, test 1, 2.
Yeah, I think it's
1, 2. Oh yeah. Okay. Cool.
So we'll start in 1 minute.
Okay. And by the way, it's fine. It's fine if I'm like walking around here, right?
Yeah.
People normally do that. Okay. Cool.
So actually, I set up the camera so that everything from here to
Like,
there is covered.
Oh, from here. Okay, so I should not
Not
like
the audio,
pass like.
yeah.
Okay. But is this fine?
You can see it here.
Okay. Cool. Oh yeah, I see. Okay.
Yeah, actually, the audio
Okay.
is also covered. Good.
Okay. Yeah. So unless. Okay. Cool.
Okay, good afternoon, everyone. Welcome to this week's iteration of AI4OPT seminar. Today we have Dylan Foster from Microsoft Research New England. Dylan is a senior researcher at MSR New England. And before that, he was a postdoc at MIT and he got his PhD in computer science from Cornell. He works on problems at the intersection of machine learning and decision making, and more recently on reinforcement learning. He's received several awards, including the Best Paper Award at Colt 2019, Best Student Paper Award also at Colt in 2018 and 2019. And today he's going to talk to us about statistical complexity of interactive decision making. So Dylan, the floor is yours.
Great. Thanks a lot. And yeah, thanks for having me. Yeah, as Siva said, this is going to be a talk about interactive decision making. And when I say this phrase, interactive decision making, what I'm really thinking about is problems where we're controlling some kind of agent or learner who is interacting with some kind of unknown environment and trying to make decisions on the fly. Like, what signal do I send to my robot's actuator? Or, what treatment do I give to a patient? And what I'm really going to be focusing on in this talk is problems where we're trying to do this in a data-driven fashion. Like we're trying to learn to model the environment as we go so that we can improve our decisions. So interactive decision-making, this is a very broad problem. There are many different ways that you can formulate this problem and try to tackle it depending on the problem domain. So, contextual bandits, this is a formulation that's widely applied in like online recommendation. reinforcement learning and control. These are much more general formulations that you see applied across domains like robotics. And there are many other interesting formulations that are studied across operations research, personalized medicine, and so on. And so the question we're going to explore in this talk is, given that we have all these different domains and all these different ways of modeling the decision-making problem, can we get something like a unified approach to designing algorithms and understanding, like sample complexity or statistical considerations? This way, when we encounter new problems, in the wild, we can focus our effort on modeling, and we don't necessarily need to start from scratch on algorithm design. And so with that in mind, the game plan is going to be as follows. So I'll start by introducing the formal model for this decision-making problem and kind of highlighting some key challenges. Then I'm going to introduce a new approach to solving this problem, and we'll see how this leads to new algorithms and new guarantees through a bunch of illustrative examples. So I'll just dive right in. So in this talk, because I want to be able to sort of discuss many different types of decision-making problems, we're going to adopt a general framework, which we call decision-making with structured observations. And you can just think of this as like a convenient language for talking about many different decision-making problems in a unified fashion. So the way this is going to proceed is we'll play for capital T rounds, where at each round, little t, we're first going to select a decision pi t in this set big pi. So big pi is like our decision space. And then based on this decision, we'll receive some reward, and we'll also receive some kind of auxiliary observation or signal. And our goal will be to maximize the reward as we're going using the data we collect. So if you've ever worked on bandit problems, this should look pretty familiar. I'll show in a moment that this can actually encompass even things like episodic reinforcement learning. But first, I just need to get through a few more details on the setup. So first of all, we're going to be considering a stochastic version of this problem, where we have what I'll call an underlying model M star that generates the data. And this is just a conditional distribution. So M star here is a conditional distribution that maps the decision you make to a distribution over rewards and observations. And all we're assuming is that when we pick the decision pi t, the reward and the observation are drawn from M star, evaluated at pi t. And M star here is what you should think of as representing like the underlying environment, right? Like this is my reward distribution, or maybe this is like an MDP if I'm doing RL. So we don't necessarily know M star. The only way we can learn about it is by interacting with it. But what we are going to assume is that we have what I'll call an underlying model class script M, which is just a set of these models. And this is something that we'll think of as encoding our prior knowledge about the problem. In the same fashion that like if we were doing statistical learning or like supervised estimation, the hypothesis class you choose, or like, what sort of function approximation you choose kind of implicitly encodes your prior knowledge. Okay, and then the last detail to mention here is we're going to be measuring performance through regret. And regret is just, the difference between the cumulative reward you would achieve if you knew what the best possible decision for M star was, minus the cumulative reward that you actually achieve. So here, just a note on notation, Fm of pi, for like a model pi, this is just the mean reward function. Like this is just our expected reward if we take a decision pi. And pi star here is the optimal decision for M star. Okay, so that's a bit of notation. But let's make this more concrete by looking at some examples. So the first example we can look at is just the multi-armed bandit problem. This is just a very simple decision-making problem where at each time step we pick a discrete decision, or these are usually called actions in this context, from a finite set, which I'm just calling 1 through big A here. And then based on this action, we see some kind of reward. We don't see anything else. So you can think of, for example, a setting where I'm trying to recommend treatments to a patient. My decision or my action might be what treatment do I prescribe, and my reward will be like how did they respond. And the key thing here is I only see a reward for the particular action or decision I pick. I don't see what I would have gotten using a different decision. So in our general framework, there's going to be no observations besides the reward. So the set O is just the empty set. Our decision space is going to be, 1 through big A. So A is just the number of decisions. And our model class is just going to be, let's say, like all possible reward distributions. We're not really going to assume anything on the rewards, maybe beyond some like basic regularity condition, like they have reasonable tails or they're bounded. Okay, now moving on. Bandits is a setting where, as I said, we don't usually assume much about the reward, but we do usually need to assume we have a small finite set of decisions. But by changing what our model class is, one can also consider settings where we maybe have a very big or like continuous or infinite set of decisions, but we make some kind of structural assumption that will allow us to generalize across them. So linear bandits, this is a setting where my decision space is perhaps like a continuous subset of R to the D, but we're going to assume that the reward functions are linear in this decision so that we can kind of extrapolate across the reward landscape. So the way you encompass this in our kind of general framework here is we're just going to restrict all the models in script M to have linear rewards, right? Which is pretty natural. And this is just one example, of course. So there are many other, different structural assumptions you can place on the rewards. Another very well-known one is like non-parametric bandits. Like this is a setting similar to the one up here, but where we only assume, for example, that rewards are like Lifshitz or Holder continuous. So weaker assumption. Okay, now moving on. So far, I didn't talk about these observations at all. And kind of the canonical setting we'll look at where these are important is reinforcement learning. So we're going to look at an episodic finite horizon RL setting. And in this setup, models are going to be Markov decision processes. So here, a model M, this is going to have a state space S, an action space a transition probability distribution PM, a reward distribution RM, and an initial state distribution, which I'm calling D1. And big H here is the horizon. So that's a model, and what the process for like sort of generating the rewards and the observations for this model, this is going to work as follows, and this is just going to be an episode in the MDP. So we're going to draw the initial state distribution, or we'll draw the initial state from the initial state distribution. And then for little h equals 1 through big H, we're going to select an action by applying some kind of policy to the current state SH. And then based on the current state in our action, we'll have some reward sampled from the reward distribution, and we'll sample the next state from the next state distribution. So that's an episode. And when we view this in our general framework, we're going to be playing mini episodes, so capital T episodes. And so at each episode, the decision we make will be like what policy we play. So what is this mapping pi? And then based on this policy, our observation will be the trajectory that this policy generates. So the sequence of states and actions and rewards that we get by running it for an episode. And then of course, our goal is just going to be to optimize the total reward within each episode. All right, so that is how you can view RL in this framework. The main thing I want to emphasize here is, when we do this, your model class M, this is encoding, what you think your transition probabilities or what you think your rewards look like. So like, what are the dynamics of your system? And there's a huge amount of flexibility in how you do this. So, there are classical examples like, MDPs with finite states and actions, or MDPs with linear dynamics, like the LQR problem. But, there's a huge number of, let's say richer structural assumptions that have been explored, both classically and in the last few years. Okay, so to summarize, the reason why we're going to adopt this kind of general viewpoint is just that it gives a concise way of talking about what you can see is a very broad class of problems with many, many options in terms of, what are the exact modeling assumptions you make. In general, what kind of modeling assumptions work best for a given application, this is going to be very domain specific. We don't necessarily want to have to start from scratch every time we're faced with a new domain or application. And so the question I'm going to explore in this talk is it possible to have something like a unified notion of problem complexity that can, capture what is the optimal statistical complexity sort of for any model class you might want to work with. And when I say statistical complexity here, really what I mean is what is the best regret you can achieve as a function of this model class script M and the time horizon T. And sort of the point here is what we would like to hope is that if we had such a notion of problem complexity measure, this could, guide us in designing algorithms and perhaps guide us in, even towards general algorithmic principles so that we don't have to start from scratch every time. Okay, so to motivate the results I'm going to present, I want to try to give a sense for why, getting a handle on the statistical complexity of like general decision-making problems is challenging. And what I kind of want to emphasize here, or like the main conceptual point I'd like to get across is that this is really a combination of both algorithmic and statistical challenges, and these are really fundamentally intertwined. And the way I'm going to try to do this is by going through just some simple examples of different decision-making problems and kind of looking at what makes them easy versus hard. Okay, so to start, we're going to look at a kind of bandit type problem where the only observations are rewards, and my goal is just to maximize, some reward function. I'm displaying the model class we're working with up here, and so this just has 3 models, M1, M2, and M3. And this plot over here is just showing the mean reward function for each model. Okay, and so this particular model class, this is an example of a like super easy problem. So what you can see here is, even though these models, they all have different reward functions that are, varying in different ways across the landscape, they actually all agree on what like the maximizer is. Like they all agree on the optimal decision. So, if I tell you in advance, like the true environment or the true model you're interacting with is in this class, the optimal algorithm is very simple, right? It's just you commit to playing this decision right here and you don't do anything else. So there's no need to explore at all. You can achieve 0 regret. So that's an easy problem. Now let's change it a little bit. So now I've moved these curves around a bit. And now you can see that the 3 models in our class all have distinct maximizers. And so this is an example of a harder problem. So, now I actually do need to kind of explore the landscape and try to find the maximizer, from samples. And, in general, the number of samples I need to find the maximizer, or like, the best regret I can achieve, this is going to depend on, how many possible maximizers there are. So this is a harder problem. Okay, now we'll look at one more example. And this is going to be very similar, but I've just changed the reward functions a little bit. So like if we look over here on the right, let me first say these still have distinct maximizers, but there's one decision over here on the right where all of the functions take very different values. And so if I know that they're in this class in advance, what I can do is just play this decision right here a bunch of times, estimate the value. And from this, I can infer what the underlying curve is, right? Like if it's high, I know it's blue. If it's low, I know it's green. And once I know what the curve is, I can just jump over to the optimal point for this curve. So, again, just by changing this model class a little bit, I've ended up with a problem where I really don't need to explore very much at all. Okay, and so to summarize, if we want to understand like what is statistical complexity and what makes problems easy versus hard, there are many different considerations we need to take into account. Like, do we have many possible optimal decisions versus few optimal decisions? Does a given decision, only reveal information about its own reward, or can we somehow share information? And again, the real point to take away here is this is tied to algorithm design. So for the examples we just saw, like it wasn't just that they were, easy versus hard. Like the optimal rule for selecting our decisions for each example was completely different. So this is much different from like, say if we were looking at like statistical learning or supervised learning or estimation, where usually we like fix an algorithm, like, just taking the model that best fits our data or doing SGD. And, how that algorithm generalizes, that might depend a lot on the different problem, but usually the algorithm itself is fixed. So here, here we really need to think about different algorithms depending on the problem. And just to drill down on this even more, these issues are really just the beginning. So like for the examples I showed, we really only cared about the mean reward function. But in general, even things like the noise in the reward distribution can like leak non-trivial information about the problem instance. Like if I tell you that, you know, for the environment you're interacting with, you know, the optimal decision always has Bernoulli noise and everyone else has Gaussian noise, like this is something that algorithms can exploit to do better. And so, you know, any notion of problem complexity needs to be able to take this sort of thing into account. And these issues are only amplified when you go to problems like RL, where you have decision spaces that are, you know, very large, but also very structured. And so I think in light of these challenges, it's very reasonable to ask, you know, is it even possible or like realistic to hope for some kind of, you know, like interpretable complexity measure that can, you know, meaningfully capture the statistical complexity for all these different problems? But what I'm going to show now is, okay, in some sense, the answer is yes. So we have a new complexity measure, which is, you know, both necessary and sufficient to achieve low regret or low sample complexity for any problem. And, you know, beyond just giving a notion of problem complexity, this is going to kind of come with a unified approach to designing algorithms. Any questions before I move on? All right, cool. Okay, so let's get into this result. Oh yeah, question.
Thank you. Yeah, so maybe from my understanding is that you are trying to find a complexity related to data, or it's not like model dependent, but data dependent.
This is mainly like model dependent, but this is like related to data in the sense that, like, you know, how well you can do given the data that you're able to like observe, right? This depends on what the models look like. Like more complicated models need more data to solve them. Yeah. But I guess just to be clear, what we're going to be looking at this talk is mainly like sort of mini-max notions of sample complexity. Like once I pick the models I'm working with, what's the best I can achieve in the worst case? Cool. Okay, so I'm going to just dive right into this result. But first, let me just explain kind of where we're going. I'm going to kind of give the high-level results around this, you know, this complexity measure and algorithm, and then in the rest of the talk, I really just want to go through a bunch of examples to, you know, just get a sense for how this thing behaves and what it's doing. Okay. Okay. So what I'm displaying here is this complexity measure that we call the decision estimation coefficient, or the DEC. There's kind of a lot going on here, so I'll walk through step by step and start building some intuition on this. So this DEC, this is a complexity measure that has 3 parameters. So it's going to depend naturally like on our model class script M. It's going to depend on what I'll call a reference model, M bar, which will be in this class. And it will also depend on a scale parameter, gamma. And we'll explain what all these things mean. So this DEC, this is the value of a like min-max optimization problem. And the way you can think about this is this min player, which can kind of represent the learner. They're trying to find a distribution P over decisions such that for a worst case model in this class, M, chosen by the max player, what they want is for their regret under this model, like the instantaneous suboptimality of their decision, they want this to be bounded by a notion of like information gain relative to this reference model. Okay, so when I say information gain here, we're looking at Hellinger distance, which is this information theoretic divergence. You can think about KL if this is more familiar, like the difference between these is not going to be super meaningful for the results I'll present. But what this is looking at is for the decision we sample here, what is the distance between the distribution over observations under M and the distribution under observations for M bar. So if you want your information gain to be big, you want to pick a decision where these lead to very different distributions. That's like the TLDR. Okay, so that was kind of a mouthful. Let me just say this again more succinctly. The way to think about this problem is this min player is the learner, and what they want to do is, in the face of like an unknown environment, which is what this max player represents, they want their regret to be, controlled by information gain. And they want to trade these things off. This parameter gamma is just kind of modulating the trade-off here. Like if gamma is bigger, I care about information gain more. If it's smaller, I care about regret more. Okay, we'll go into a bunch of examples of this, but just a couple notes before we move on. So first of all, what we're really going to care about here is just the max of this thing over all reference models in the class. I'm just going to denote that by DEC of script M. Okay, and so again, why do we care about this thing? Well, what I'm going to show you is this leads to both, upper bounds on regret, so algorithms, and lower bounds on regret. I'll start with the lower bounds. So what you can show is that for any model class script M, the best regret that can be achieved by, let's say, any algorithm is lower bounded by this DEC for an appropriate choice of this scale parameter gamma. I'll go into more details and show the precise expression in just a minute, but what I'm doing here is just giving a teaser. So what this table is just lower bounds for all of the standard kind of like bandit and RL problems in the literature. And these are all just special cases of this general lower bound. Like these are what you get by saying, okay, this is the model class I'm working with, like multi-armed bandit, linear MDP, tabular RL. This is what you get by plugging these classes in and just seeing how this DEC behaves and plugging it into our general lower bound. And I think one thing that's especially cool here is, this is not just recovering optimal rates for problems like multi-armed bandits that are known to be tractable. This can also recover strong impossibility results. So things like exponential lower bounds for problems that are known to be intractable. Okay, now, as I said, I'll give a little more detail about this in a second, but first I want to say a little about the upper bounds. So on the upper bound side, there's a simple kind of meta algorithm associated with the DEC that we call estimation to decisions, or like E2D. And what you can think about this is it's actually like a reduction that allows you to reduce the decision-making problem to the problem of like supervised learning or estimation. So I'll just go through this. This is like a 3-line algorithm. It's very simple. So we're going for capital T rounds. That's just the number of rounds in our decision-making problem. And so at each round, the first thing we're going to do is we're going to get some kind of estimator M hat T by running some kind of like supervised estimation algorithm on all the data we've gathered so far. So all the rewards and observations we've gathered so far. This can be, whatever estimation algorithm you want, like, but you should usually think of something like, say, like MLE or like regression. So once you have this estimator, which is, this is really trying to estimate what is M star, which you don't know. Once you have this estimator, all you're going to do is plug this into this decision estimation coefficient in place of the reference model. You're going to compute the distribution P that minimizes this thing. And then you're just going to, pick your decision by sampling from this distribution. Okay, and that's going to give you some new data. So it'll give you a new reward and observation. You're then going to go and use that to update your supervised estimation algorithm again. Okay, and so what you can show is if you run this algorithm, your regret is controlled by this DEC itself and some notion that's looking at like how well are you actually doing at estimating the underlying model. So to get into detail on this, we're going to define this quantity est of t here, and this is just going to be the total like Hellinger distance between the true model M star in our class and these like estimators that we're getting from our estimation algorithm under the data that our algorithm is generating. And what you can show is that your regret, if you run this algorithm, it's going to be bounded by, okay, this DEC at scale gamma times t plus gamma times, this estimation error. So, again, if your DEC is small, the estimation error is small, you're doing well. Okay, and one thing I want to emphasize here is, keeping this estimation error small, this is something you can do like provably. So like even though I'm having to do estimation on data that's being generated in a dependent fashion, we can keep this small by using tools for like online learning, and in particular like sequential prediction with the log loss. So just to give some examples, if I have a finite class, I can get something like, say, log number of models as my estimation error. If I do have a parametric class, I can get something like, dimension of the parameter space as my regret. In general, what you expect here is something that's going to reflect, the statistical capacity of your class. So like the optimal rate for estimation. To make this all more interpretable, though, I want to actually come back to the lower bound. So what I'm displaying here is the kind of quantitative version of our lower bound. What this is going to say is, yeah, for any model class script M, the best regret you can achieve, this is going to be lower bounded by the min of two quantities. So one is, again, this DEC at scale gamma times t. The other is gamma itself, and you can take the max over gamma here. Okay, now, if you run a slightly more refined version of the algorithm I just showed, you can get an upper bound that, okay, looks very similar to this if we put them side by side. So in fact, this is the same expression. The only difference is the presence of this estimation error term. So this is saying like up to, what is the like estimation capacity of your class, you're getting upper bounds and lower bounds that match each other. But let me finally give an example. So if we come back to this multi-armed bandit problem where we have A decisions, you can show that the DEC at scale gamma, it looks at like something like A over gamma. And you should think about this in the regime where gamma is large. So gamma is like bigger than 1, it's growing with t. So this is shrinking as gamma grows. If you plug this into the lower bound, what you're going to get is like min of AT over gamma and gamma. The optimal choice of gamma is to balance these, and this gives root AT as a lower bound, which is like the min-max rate for this problem. So that's like the optimal rate. Let me just give one more remark here. This DEC gamma, epsilon gamma, this is what I'm calling like a localized version of the DEC. So this is where you're kind of restricting to some subset of the class. I'm not going to go into detail about this in this talk, but I'm happy to, get into the math for that offline. But this is the same quantity appearing in both the upper and lower bounds. Okay, but to give the broader picture, because you have these lower bounds and upper bounds that match up to estimation, you can actually extract from this, a characterization for just when is learning possible at all. And this is going to say, under appropriate regularity conditions, you can get non-trivial performance, like non-trivial regret, if and only if this DEC has like polynomial decay as a function of this gamma parameter. Okay, I'm just going to give a few more remarks, and then I'll get into a bunch of different examples so that we can really start building some intuition. So first of all, just some technical remarks. Yeah, as I said, one question you might be wondering is like why Hellinger distance? This is not too important. So like if you make like the most mild possible regularity condition, which is just that the models we're working with have bounded densities, then you can also do everything with KL up to perhaps like logarithmic factors. So this is just really, you can think of Hellinger as like KL that behaves reasonably at the boundaries of the simplex and like doesn't blow up. So this is a more kind of like operational version of KL. That's how I like to think about it. Okay, and then I'll also just mention, all of the statements I've presented so far are informal. There are different gaps between the upper and lower bounds, which lead to things like, say, differences in like polynomial factors. I do not have as much time as I would like to get into detail about these, but I'm happy to chat about these more offline. Okay, now zooming out. So one reason why I find these results exciting is because they're giving a way of taking supervised learning or estimation, which is this passive problem, and bridging the gap between this and like interactive decision making, which is this like active problem, right? So the point here is, you can pick whatever algorithm you want to do like estimation or learning, and as long as you're doing this estimation well, this like estimation to decisions principle, is going to take care of the rest. And so this is giving some kind of like paradigm where when we encounter new decision-making problems, we really just need to focus on A, like what model works well and how do we do estimation well, and B, just, how do you compute the distribution that solves the DEC? Like as long as you can do these things, you're good to go. Okay, and then the other remark I wanted to make is on a connection to like statistical estimation and like Lecombe theory. So if you're coming from the stats side, you might be familiar with this notion of like modulus of continuity in statistical estimation. So this goes back to the work of Donahoe and Liu in the 80s. Many people have worked on it, in the years since. But what this is doing is, this is looking at the problem of non-parametric estimation, where I'm just getting a bunch of IID samples from some unknown distribution passively, and I'm trying to estimate some functional of this distribution. So this modulus of continuity, this is a complexity measure that is trying to get at the statistical complexity of this non-parametric estimation problem. I'm displaying it right here, kind of in notation that emphasizes the similarity to the DEC. What this is doing is it's looking at, okay, suppose I'm in like some Hellinger ball around a reference model. What is the worst case error in the functionals I'm trying to estimate? So Donahoe and Liu, they showed that this gives upper bounds as well as lower bounds for this non-parametric estimation problem under appropriate technical conditions. And we really kind of think of like the DEC as giving a decision-making analog of this complexity measure, and in some sense, something that allows us to, like lift this tradition of like, Lecombe theory to these interactive decision-making settings. The main difference, and what really makes this like a rich problem, is that because it's a problem where we have to make these decisions actively, we have a min-max rather than just a max. Okay, and while we're on this topic, I'll just mention there's a few other complexity measures that have been explored more in the decision-making context that you may have seen before that also, consider different trade-offs between regret and information gain. I'm not going to get into detail on these, but yeah, you can check out our paper if you want to kind of understand, what are the connections. Okay, with that, I think I've said all I wanted to say about sort of the high-level results. So now we can do, what I really wanted to do from the beginning, which is, give some intuition as to like, what does this DEC actually look like and how does it adapt to the complexity of different problems? And we're going to do this by walking through a few different examples. So we're going to first look at some examples that show how this thing can adapt to, structure in the reward landscape. Then we're going to look at some examples that are more information theoretic in nature. And then finally, we'll see what happens when we kind of, have like non-trivial observations, so things like trajectories, and apply this to reinforcement learning. And hopefully, assuming there's enough time, I'll also be able to give a sense for, what this looks like when we go, beyond like finite state action RL settings to like RL settings with function approximation, like high dimensional settings. Okay. So we're going to start by just coming back to this multi-armed bandit. Again, this is just a setting where we've got a finite decision space, 1 through big A. The only observations are rewards. I'm displaying the full DEC here, but what it actually turns out is that for this setting, you can simplify it by replacing the Hellinger distance with just the squared error between the means. So this is equivalent to the original version up to constants. And the reason why this happens is just that we're not really putting any assumption on the noise distribution. So in the worst case, this max player can just put like white noise, and this makes it so that, everything except the mean is uninformative. So the mean kind of serves as a sufficient statistic. So I mentioned before that the DEC scales as A over gamma here. And what I want to do now is give a sense for how do you like upper bound this thing? Like how do you show that this is at most A over gamma? There's two different ways that you can do this, and I'll give a kind of quick overview for both of them. So the first technique we can use here is something that we call inverse gap weighting. And this is just a particular choice for this distribution P in like the min player is choosing when we're looking at this min-max problem. So the way this is going to work is we get this reference model M bar, we fix our scale parameter gamma, And the way we pick the probability for each decision pi is we assign it a probability that's inversely proportional to the gap between the estimated reward of the greedy action that just tries to maximize fm bar. Fm bar here just again is the mean reward for fm bar or for m bar. So it's just the gap between fm bar pi m bar and fm bar of pi, where pi is the decision we're looking at. Okay, so that's why this is called inverse gap weighting, right? It's inversely proportional to the gap. We're scaling the gap by gamma here, and then we're picking a like normalization constant lambda so that these p's actually sum to 1 and are indeed a probability distribution. Okay, so what you can show is actually this is the exact minimizer for the DEC. So if you go and do your Lagrange multipliers and like check first order conditions, this is what will pop out. And this, this is going to lead to this A over gamma bound. And like the high level intuition here is pretty simple. Okay, so if you think about what happens in extremes as a function of gamma, when you set gamma to 0, this gap goes away and this just becomes like the uniform distribution. So this is just kind of exploring. And if you set gamma to like infinity, this is only going to put mass on like the greedy action. So you're like purely exploiting. But in general, you're kind of interpolating between exploring and exploiting in an adaptive way that depends on what these estimated rewards look like. But the precise form of the probabilities here is very important because this kind of gives like a heavy tail distribution. Like, so just doing something like say softmax on the estimated rewards does not work here. Okay, so that's one approach to showing that the DEC is bounded for this setting. Another approach, which is perhaps less obvious, is to appeal to Bayesian methods. Okay, and when I say Bayesian methods, this is maybe sounds a little confusing because we've only been working in like a frequentist setting up until this point. But the idea is that there's actually like a Bayesian counterpart to this DEC whose value is equivalent to the original DEC. And this is a consequence of the min-max theorem. So the idea here is you start out with this DEC. You can kind of convexify the max player here by switching from a max over models to a max over distributions over models, and then sampling the model from the distribution right here. So mu here is our distribution over models. And once you convexify in this fashion, this becomes like a convex concave minimax problem. So you can use the minimax theorem to swap the order here, where now the max player is picking this distribution first, and the min player is able to choose their distribution with knowledge of this thing. And so this kind of has a Bayesian interpretation where you can think of mu as like a prior over models, and you can pick your distribution with knowledge of this prior. Okay, and so the idea is, yeah, like this is equivalent in value to the original DEC, but now you can appeal to like Bayesian techniques, so things from like say Bayesian bandit and RL literature to try to bound this thing. One example is, there's this very well-known classical strategy called like Thompson sampling or posterior sampling. What this does is it just picks your distribution P to be the distribution induced by, drawing a copy of M from this prior and just playing the optimal decision for M. And this you can show also leads to an A over gamma bound on the DEC. Many of these prior works in like Bayesian bandits are actually just implicitly kind of showing that this DEC is bounded here. But one important thing to understand is this is not like a constructive strategy or like a constructive algorithm. Like this is a P that will minimize the Bayesian DEC, but that does not mean that it, says anything about the P that, minimizes the original DEC. It just tells you that the value is bounded. Okay, I want to move on to another example. So this is going to be what we'll call like full information online learning. And this is going to be similar to bandits, but now instead of just seeing the reward for our own action, we're going to get an observation that tells us the reward for every other possible action we could have taken. So now we actually get to see like the full reward function at every step, or at least a noisy sample of it. We don't just see our own reward. And this is a much easier problem because you don't need to explore anymore. So what you can show here is that the DEC is both upper and lower bounded by 1 over gamma rather than A over gamma. And this is just going to lead to like a root T lower bound rather than a root AT lower bound like we saw for bandits. And the intuition behind this is very simple, right? It's that you can just you can just be greedy because the information you get does not depend on what action you select. So you don't need to balance information and maximizing the reward function at all. Okay, now bandits and full information, these are kind of at two extremes in terms of like how much information about the reward function you get. We can also come back to these like structured bandit problems, which kind of lie in the middle. So if we come back to this linear bandit problem, just to remind, this is a setting where the decisions live in R to the D, and we assume the reward functions are linear. Here, you can show that the DEC grows as D over gamma, rather than like number of actions over gamma. And this is kind of reflecting the fact that there's really only like D effective directions that matter when you assume the rewards are linear. Like once you explore along a well-chosen basis, you can kind of extrapolate to other actions you might not have seen before. And you can kind of combine that idea with the techniques that I showed in the bandit setting to like derive this bound. And this is going to lead to like a root DT lower bound rather than root AT. Now, one comment here is the scaling we've seen so far where the DEC seems to grow as like some notion of problem complexity over gamma, like this is very common, and you see this from many other model classes. But not all model classes have this behavior, and you have different scaling for problems where the optimal rates are worse than root T. So if we come back to this non-parametric bandit setting I showed in the beginning, where we only assume that the rewards are Lipschitz and nothing else, here you can show that this DEC grows roughly as like 1 over gamma to the 1 over D. Okay, really 1 over D plus 1. But the important thing to understand here is as you take D larger and larger, this is decaying more and more slowly as a function of gamma. And when you plug this into the lower bound, you get something like T to the D plus 1 over D plus 2, which is getting, again, like worse and worse, like so closer and closer to linear as you take D larger. And that's the minimax rate for this problem. Okay, now I want to move on. So far, these examples, we're only looking at, how did this DEC depend on the structure of the reward function? Now what I want to look at is an example that's more information theoretic in nature. Well, actually, before I move on, maybe I should just check. Are there any questions on the examples we've done so far? Yeah. 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 Right. So it depends on like how in practice you're talking about. So like in practice, like when we've experimented with these things for say like contextual bandits, the answer is you do like cross validation. But to give a more satisfying answer, you can try to like kind of also use online learning to like select this gamma on the fly. There are some cases where this provably works, but there are other. You shouldn't expect to kind of be able to optimally adapt to the gamma that's best for your problem in the science site, kind of for like statistical reasons. Yeah. Right, that's a great question. So I guess the thing is, this is a question of like, how are you setting up the problem? So the way we're setting up the problem here is we know what the model class script M is in advance. And the optimal gamma for the bounds we're showing here, is just a function of this model class. So in a theoretical sense, the optimal gamma is just the one that minimizes the upper bounds I've shown here, right? So but that's my point is like in practice, that's maybe a different question from what works well in practice, I guess is what I'm saying. Yeah. Yeah. Yeah, that's like the right thing to do in theory. I'm just saying like in practice, that's probably a little pessimistic. Yeah.
I have a quick question.
Yeah.
So in the multi-amp bandit setting, I think you briefly mentioned about the connection to posterior sampling. Is there any connection to UCB like algorithms?
Yeah, there actually is some connection. I don't have slides on this, but I can tell you a little bit more about this offline. Yeah. Like, okay, I guess the TLDR is you can combine in kind of what I'm showing here with like confidence set type ideas where you do this DEC thing restricted to some confidence set, and that kind of subsumes UCB in these sorts of algorithms. And that's actually necessary to get like the tightest possible guarantees. Yeah.
Thanks.
Yep. Okay, so let's come to an example that goes kind of beyond just looking at reward functions. So, okay, I promise this will be the last bandit type problem, by the way, but this is going to be, again, a setting where we have a finite set of actions, but now I'm going to assume that the rewards are structured. And what I mean by this is, for any model in our class, we're going to say that the reward distribution is Bernoulli with some like positive bias if we take the optimal decision, and Gaussian with mean 1/2 if we take a suboptimal decision. So if you know this in advance, this is an easier problem than regular bandits, because if I take the optimal decision, I'm going to see like a reward of 0 or 1 almost surely, because it's Bernoulli. If I take a suboptimal decision, well, it's Gaussian, so I'm not going to see a reward of 0 or 1 almost surely. So yeah, if you tell me this in advance, like an algorithm is just try every arm, look at which arm you saw either a 0 or 1 on. That's the optimal arm, so you can commit to playing this. So the optimal sample complexity here is just like A. And what you can show kind of using this intuition is the DEC actually has some like threshold behavior where it goes to 0 once gamma's above A. And this leads to, yeah, just a lower bound of A rather than root AT, you know, which is like the right complexity for this problem. And the important thing to understand here is, like here, working with Hellinger, or like, again, KL would be fine, is very important. Like Hellinger and KL can instantly tell the difference between Bernoulli and Gaussian. But if I were just looking at, say, like the difference between the mean rewards, then this looks the same as like a regular bandit problem. So this would not have the right behavior. And I'll just mention, you can generalize this idea of where like there's information encoded in the noise very far. So you can think about, you know, settings where I have Gaussian noise, except that when I go like down 100 bits into like the binary representation for the rewards, I've like encoded some arbitrary string of bits, right? So this is actually saying, you know, if you think you can solve bandit problems with like arbitrary structure in the noise, really you should just be able to solve problems where you get arbitrary like auxiliary signals. And so kind of the point of this general framework we're looking at, where you explicitly have observations, you know, is just to make this fact explicit because it's useful to be able to work with observations. And so, you know, with that in mind, we'll look at tabular RL, which is like the most basic setting where these observations really play an important role. Just to remind here, in this setting, you know, models M in this class, these are going to be MDPs with horizon H. We're going to have a finite state space S, finite action space A, and then our decisions will be, you know, what policy to run in our MDP for the episode. Our observation is the trajectory you get. So for this setting, you can show a lower bound on the DEC, which scales as HSA, so horizon times number of states times number of actions over gamma. This gives a root HSAT lower bound. So this is saying, you know, if you do RL and you don't really assume anything except that, you know, the state and action space is finite, then just the size of these spaces is going to be what determines the complexity for a problem. And you can get similar upper bounds. So not exactly matching, that's a good open problem, but you can get something like poly H times SA over gamma. And the way you can get this is by adapting the techniques I showed for bandits. So both this inverse gap weighting technique and this posterior sampling. I'll just give a quick overview of like how you adapt this inverse gap weighting, because I do think it's useful to understand how this technique can kind of extend to, you know, more general problems. And the basic idea here is, you know, you're going to do the same strategy where you assign, you know, decisions probability that's inversely proportional to their estimated gap. But you're going to do this in like policy space. The only issue is there's like a lot of policies. There's exponentially many. And if you do this with all of them, you're going to explore too much because you're not really sharing information at all. And so the idea is instead to do this inverse gap weighting to a small set of representative policies that we call a policy cover. So what I'm showing here is like how you compute this policy cover. So this is what you do, you know, when you have your reference model M bar and your parameter gamma, and you want to compute this distribution. So the idea is for each kind of like tuple of horizon, state, and action, you're going to compute a corresponding policy pi HSA. And this is maximizing the ratio of two terms. So the top term is just the probability that you visit this state in action. This is where the covering part is coming from. Like I'm trying to cover all the states and actions, but I'm trying to balance this with my estimated regret. So like the idea is I'm trying to balance like covering the MDP with making sure that I am not, exploring too much and incurring bad regret. So you compute the policy that, solves this problem for each HSA. You're going to do this for all of them and put them all together, and that's going to give you your policy cover. And then the idea is you just do the exact same inverse gap weighting I showed before, but only to the policies in the policy cover. And this is what's going to give you this like poly HSA over gamma bound on the DEC. The intuition I think is pretty clear here. Like you want to make sure you're exploring the MDP and reaching states you haven't seen so far, but you want to make sure you're not incurring too much regret while you're doing this. The main thing that's subtle is, you care about exploring the true MDP, but what I'm actually doing up here is, maximizing the probability of reaching these states in the estimated MDP. But you can kind of use change of measure type arguments to show that like, one of two good things happens. Like either this leads to good coverage on the true MDP, in which case great, or it doesn't, but that means there must be some error in estimation, and that can actually only happen so many times if I'm using like a consistent estimator. Okay, so those were kind of like the main illustrative examples I wanted to get through. I'm just going to give a very quick teaser for what happens in more general RL settings, and then we'll call it a day. So when you go beyond like these like tabular RL settings, like these finite state action settings, the point is you want to be able to handle these like big continuous state spaces. And you kind of want to be able to like generalize across states, like generalize across the MDP. And this of course means I need to be able to use like modeling and function approximation. Like I need to be able to put modeling assumptions on my transition dynamics that will allow me to do this. And there's a few different ways you can try to set this problem up. So one way is what are called model-based methods in RL. This is pretty intuitive. Like this is just going to be settings where your model class M is directly parameterizing the transition probabilities. So like, if I am working with like a linear dynamical system, M might be just parameterizing like what are the system matrices. So it's model-based methods. The other kind of class we'll look at here are what are called like value-based methods. So these are settings where you're not trying to directly model the transition probabilities. Instead, you're going to try to model like value functions or like Q functions for the MDP. Where, okay, so here a Q function is just saying, if I start in some state in action and then run some policy until the end, what's the expected return? And usually what you do in value-based methods is, have some class of Q function estimators like linear models or neural nets or whatever. You try to estimate these Q functions. So there's no like explicit model class when you set up the problem this way, but there is an induced model class, which is just, all the MDPs that are like consistent in some way with, whatever Q functions you're trying to use. Okay, so there's many, many examples of like both of these methods. More than one can cover in a single talk. But the interesting thing is there's also many like general structural conditions which try to like subsume various classes of, MDPs that are tractable. So, this has been a very active area of research, I would say, especially in the last 5 years. Like this Bellman rank paper is really kind of what kicked this line of research off. So these are all different like properties of your MDP that you can look at that kind of tell you, okay, under these conditions, you get low sample complexity. What you can do is show that like this DEC is, can be bounded in terms of all of these different complexity measures. So just to give one example here, if your MDP has like low Bellman rank, which is somehow saying that like, the number of possible effective state distributions is not too large, this means, that your DEC grows as something like Bellman rank over gamma. And so this leads to upper bounds. But I think the cool thing in this setting is, this also leads to like lower bounds. And that's really the difference between these sort of previous complexity measures and what we're doing here is this is not just a sufficient condition, it's a necessary condition. And so in particular, we can recover some like recent results that, show that if you try to use value-based methods and you kind of don't place strong enough assumptions on the MDP, things are not tractable. Okay, I think that's just about all of the main results I wanted to cover. So I'm at the end, so I'll just go ahead and summarize. So we saw that this decision estimation coefficient This leads to, necessary and sufficient conditions to get like low regress. And, I find this exciting because on one hand, this gives something like a systematic way of designing algorithms when we encounter new problems. But it also gives, kind of a unified perspective on like many existing approaches, both like algorithms and models. And I'll just mention a couple future directions. So first of all, I think like thinking about practical algorithms from this framework. So if you specialize to reinforcement learning with Horizon 1, which is like contextual bandits, here we've actually already seen that the algorithms that come out of this framework are like very practical and actually have like state-of-the-art performance in some sense. And I'm just giving like a teaser here, but like these are in this VW library for like, interactive online machine learning. These are like very easy to, download and get up and running if you want to try them out. So yeah, for contextual bandits, like, things are very nice. But I think there's still a lot of work to be done in terms of, extracting like practical algorithms here when you go beyond Horizon 1, right? So for like, RL problems that truly have a long horizon. And this is kind of a combination of both like finding out, what are like good modeling assumptions in practice, and also, like doing things like, efficiently solving this DEC for such models and modeling assumptions. So I think that's a really interesting question. More broadly though, kind of the vision here is just, building like a theory for decision making that like parallels our understanding of these classical settings like learning and estimation, meaning things like, how do you understand problem complexity? What are the like general algorithmic principles? And that goes beyond the core framework in this talk. So things I'm like thinking about a bunch here are like, what happens when you have multiple agents, or like what happens when you want to learn from like logged or offline data? These are really interesting. And of course, there's like, tons and tons of technical questions and open problems, like more than I have time to discuss. But yeah, happy to tell you about any of these offline. But I think I should probably stop there.
Questions?
Hi, great talk, by the way. So one question I have is, so I'm not an expert in RL, but
Sure.
If you want to apply it to an application where maybe you have an expert that has like domain knowledge, you want to implement it here, have you thought about a way to formulate that?
I mean, the natural way you formulate that is like through what model class you pick, right? So this would be something like, your domain expert comes and tells you like, maybe this class, maybe the problem application I'm trying to solve is well modeled by like, an MDP that has like low rank structure or something like this. And then you go and say like, that's my model class. How do I like solve the DEC for this thing? So that's like the obvious answer to this question.
And another question I had was, were there any like decision-making models where you found this general framework had a tough time being applied to, maybe like gaps in upper bounds or lower bounds, or?
I guess it's hard to say what it means to have like a tough time. I mean, like definitely for, many of these examples, you do have to think about it and do some math to like compute this thing. But this is the thing about having like a complexity measure that gives you like upper and lower bounds though, which is that like, if you can't bound this thing, you're kind of out of luck. Like that just means the problem isn't tractable, right? So it's certainly there are many like open problems, right? Like, if you go back to RL, I don't know what the best H you can get here is. I'm sure someone can like think about this and like write a paper on it if they want to. There are other examples like, if you go to I went too far back. If you go to, okay, I just mentioned like bandits with like convex or like concave rewards here. Like, okay, it's like an open problem in the literature. Like, what is the best dependence on the dimension you can get? Like, like the best lower bound is like D, the best upper bound is like D to the 4. But within this context, like this DEC is recovering the best that's known. But again, it would definitely take someone thinking about this a lot to figure out what the optimal dependence is. But again, like it is both an upper and a lower bound. So like, if you think you can like solve this problem, it should be possible to do it through this framework.
Since we're running out of time. We'll close the session, but you can continue chatting with Dylan. Let's
Okay.
thank Dylan again.
Thanks a lot.